Okay, there we go. We are recording. So, two main things I want to do today's class. We're going to talk a little bit more about elementary matrices, which is going to ultimately lead us to a part of the equivalence theorem. And then we're going to talk about ways to find inverses of matrices. I'm going to show you two methods to do that. That's kind of the goal. Recall some things though about determinants. So in terms of determinants, how does a type 1 operation affect the determinant?
It negates it.
It negates it, right? In other words, you can think of it as scaling it by -1. Okay? So if you perform the type 2, which means you multiply it by a non-zero scalar, what does that do to the determinant?
It scales it
It scales it by what?
by that integer k.
By the same scalar. What if you do a type 3 operation on a matrix? How does that affect its determinant?
It doesn't.
No effect. In other words, what you can do is think of as row operations on a matrix. Scale the determinant. This is how they affect determinants. Okay? They'll scale by something. They'll either scale by -1, if you do a type 1. It'll scale by +1, in other words, having no effect if you do a type 3. If you do a type 2, it'll scale by the same scalar that you used in the type 2 operation. So the effect of a row operation is to scale the determinant. So that's an important idea to know. And that will give you a lot of intuitive power when you're doing certain things and figuring out whether a proof is going to work out in a certain way. And it's also going to make a lot more things make sense that I'm going to say today. Like the fact that if you have a square matrix and it reduces the identity, I know its determinant is not zero. Right? That should make sense by this intuition. Right? So you can get away with a little more hand waving if you see that. So also recall an elementary matrix, what that is. Is how do we obtain elementary matrices?
You perform a single row operation on an identity matrix.
It's a matrix obtained by performing a single row operation. On the identity matrix. Also, the important thing is that you should recall is EA is the matrix obtained when the row operation described by E is performed on A. So this allows us a very powerful technique. So this allows us to think of row operations as multiplication of a matrix. right? Because so when you sort of talk about row operations, it seems like this thing that's ephemeral, you can't really get a handle on it. When I tell you specifically, it's multiplication by this matrix. That's something concrete that you can actually use, you can move around, you can manipulate it algebraically. You can't really manipulate a row operation, whatever that means algebraically. So this gives us an algebraic handle on things. It's a very useful technique. For example, I mentioned this yesterday without proof, that the determinant of a product is the product of a determinant. It turns out that to prove that, we spoke in terms of row operations, which we described in terms of elementary matrices. So if you read the proof in your book, for example, they used elementary matrices in order to prove that. So it gives us a very powerful technique that we can manipulate. We can think of row operations as just matrix multiplication. Right? So a row operation is really just a matrix multiplication by a certain elementary matrix. So if I want to do something to a matrix like, oh, take row 2 and add it to row 3, I can just describe that by doing that on the identity, creating some matrix, and then multiplying it. So that's really nice. So we're going to take this a little bit further today and talk about elementary matrices. And we're going to use that to prove some nice properties. So, theorem.
That's the determinant of A times the determinant of B, right?
Yeah. The determinant of a product of matrices is the product of the determinants. So what are we going to do? Okay. It's a theorem. I did introduce that as a fact, but it's technically a theorem. Elementary matrices are always invertible. And their inverses are elementary. Elementary, dear Walter. Inverses are elementary. Proof. Let E be some elementary matrix then define E1 to be the matrix representing the inverse operation. And it turns out that row operations are always actually invertible, right? You never do something that you can't undo when you're doing a row operation. So what can you do? You swap 2 rows, that's a row operation. How do you undo that? Just swap them back, right? Which is itself another row operation, right? Okay, multiply by a non-zero scalar. How do you undo that? Divide by the non-zero scalar, right? If you take a multiple of one thing and add it to another, what are you going to do? Well, just add the negative of that multiple to the row, right? So whenever we do a row operation, you can actually undo that row operation. And so that itself is you doing an operation. You're just doing the operation the opposite way. So that can be described by some elementary matrix. So then E1 times E gives us the identity, right? So I obtained E by doing something to the identity to get this new matrix, but I can just multiply on the left by that to undo whatever that guy did. That's going to give me the identity because of this fact. So this means E1 serves as E inverse, right? Because the definition of inverse says it's the matrix that when I multiply by this guy, I get the identity. So the invertibility of the arithmetic operations that we do leads to the invertibility of the matrix that represents the operation. So that's a nice thing. Elementary matrices, we can always just undo them by doing the opposite of the thing that created them. Here's another theorem. That A n by n and B n by n be invertible, then AB is invertible. If I take two matrices and they're invertible, and if I multiply them, if it's possible to multiply them, it turns out that the product is invertible. The product of invertible matrices is itself invertible. How can we prove this? In fact, I can tell you what the answer is right away. The inverse of the product is going to be, does anyone know?
The product of the inverse has been switched.
Product of the inverse is switched. This is what an old professor of mine referred to as the shoes and socks law. Right? Why? Imagine you're doing two operations. You put on your socks and then you put on your shoes. To undo that operation, you have to take the shoes off first and then take your socks off. So when you do something in one order, to undo it, it makes sense that you have to undo things in the opposite order in which they happen first. Right? We call this the shoes and socks law. I don't know if that's a thing. That's the first case I heard about such a notion. We call this the shoes and socks law. And he'd be proving things. And oh yeah, by the shoes and socks law, blah, blah, blah. And that's what he'd refer to. Transpositions also have a similar property. Right? If you take the product of the transpose of a product, it turns out it's the product of the transposes in the opposite order. But that's actually true. And let's actually do a proof. Did you have a question?
This only works for square matrices?
Well, only square matrices can be invertible.
Oh, right.
Right. Non-square matrices aren't even invertible at all. So that's why, yes. So that's good. That's something you should be paying attention to. Notice that I said the dimensions. Right. Determinants and invertibility only apply to square matrices. You can't invert a non-square matrix. Okay. So here's the proof. Assume A and B are invertible. Then A inverse and B inverse exist and are also, of course, there will be n by n matrices, which means I can multiply them in any order because the numbers will match up. So we can actually form this matrix B inverse A inverse, right? So it's not some mythical creature. I have reason to believe this exists, right? If each individual exists, then their inverses exist. These guys are square. Their inverses have to be square of the same dimensions. And so these are two n by n matrices. I can multiply them in any order I want because the inner numbers will always match up. And so I can create this guy. Then, if I take A, B, and multiply by this guy, that would be equal to, because matrix multiplication is associative, I can choose which pair I'm going to multiply first. If I multiply the inner ones, this by definition gives me the identity. Then multiplying this pair together, that of course gives me A by definition of the identity. But then by definition of A inverse, that ultimately gives me I. Therefore, this is the matrix that when I multiply A, B by that matrix, the result is I. And if I take AB and I multiply on the left by this, then by the same logic, that would give me an I here, that would give me a B inverse B here, and that would give me I. This means that B inverse A inverse is the inverse of. So if I have two matrices that are invertible, they have the same dimensions, it turns out their product is also invertible and has the same dimension. And of course, not something we're going to be concerned about now, but that also tells you something about the functions that are behind the scenes. If I have two invertible functions that go between sets of the same dimension, I can compose them, and the result will also be an invertible function that goes between the sets at the far ends. Here's another proof. Oh, well, another fact that we're going to be using. Let's take a bunch of them. Any finite list of matrices. Let this be invertible matrices of the same. Of the same size. Let's call this n. So I can say there are n by n matrices, there are m of them. Then the product is invertible. Right, so it works with two, but it also works with any finite list of matrices. I take any list, any finite length long of matrices that are invertible, their product, I can multiply them all together, and the result is going to be an invertible matrix. In fact, I can tell you what that is. A1, A2, AM. Okay, the inverse of all that product is later going to be the inverses multiplied in the opposite order by the shoes and socks law. Let's actually prove that. Ideas on how to prove this?
Induction.
Induction. So here's where induction is going to come in. Induction is nice when you have a statement where the statement evolves with the number of things you have. M is arbitrary here. It can be any finite positive integer. And so if I want to prove a statement that's true for any finite positive integer, induction is usually a nice way to go about it. So the length of this list can be literally any finite positive integer. So I'm going to do induction. Proceed with induction on M. Okay, so I'm going to do induction on the number of elements that we have here. So I'm letting Pm be the statement that A1 multiplied up to Am is invertible. So this is a statement that depends on the integer m. Of course here m is in a natural number. How does induction work?
Oh, prove for the base case.
You need to prove the base case. So for the base case, what is that? Prove that it works for the first guy. Prove that it works for 1. P of 1 is true since A1 is invertible This we get by assumption. I assumed I assume everyone here is invertible. So that's kind of okay. Let's prove it's true for 2 guys. It is helpful to note this is true at P2 by the previous theorem, right? I know the product of 2 of them is also invertible, right? i.e. A1, A2 is invertible with inverse A2 inverse A1 inverse. So we proved the base case. I'm telling you that we can note this by the previous theorem. So P1 is true and P2 is true. So we've established the base case. What's the next step in an induction proof?
Create your induction hypothesis.
Okay, what does that hypothesis say then?
That it is true for an arbitrary integer k. P of k is true.
Assume P of k is true for some particular k. Okay, so pretend the statement holds for some guy. Then what you need to do.
Show P of k plus 1.
You need to show that it's true for the next guy. So it's true for the first guy. If it's true for anyone, it's true for the next one. Ultimately, that means it's true for everyone.
Do we have to put more conditions since this is finite? We're bounding the k, right?
Well, k is automatically going to be bounded by m. I'm assuming the list, the length of the list is a natural number. So it's going to be some natural number. And there, this is some natural number. Okay, so how are we going to prove that this list now is invertible? Since P of k is true, that means if I multiply A1 through AK is invertible, and I know what its inverse is, it's the product of the inverses in the opposite order. Consider now, if we had one more guy. What do you guys think we should do? We have k plus 1 things now.
So
How do I know it's going to work for them? Yeah?
you're going to multiply by the inverse. So
Of what?
a inverse k minus 1 up to a of 1, and then each up to a1 to ak, you'll get if you multiply each, you'll get an identity matrix. So then you'll be left with an identity matrix times
Times this guy?
yes.
Okay.
And
What do we know about this guy? Of course, we're assuming that all these a's are invertible, right? So ai are invertible. Which means that last guy inverse is going to exist, and you can just multiply by his inverse at that point. Here's another way to write this down. It's a technique that's used a lot. It's just think of all these previous guys as one big matrix, right? Because when you multiply that list of matrices, you're going to end up with a matrix. Right? Very common thing to do. So in other words, I can think of this product of k plus 1 matrices as really the product of 2 matrices. And how is that helpful?
Because
I know it's true for 2 things. I'm not sure if it's true for k plus 1 things, but I know it's true for 2 things.
This is strong induction, right?
This is called strong induction, yes, technically. So in the next class, we'll go into that a lot more deeply. So it's when you prove several base cases because it's helpful. But since P of 2 holds, BAK plus 1 is invertible, and its inverse is AK plus 1 inverse B inverse. This means if you take A all the way to K plus 1, and take its inverse, what's that going to look like is, let me multiply it by this guy so you can see it. We're going to construct it. So if I take A1 all the way through AK plus 1 and multiply it by B inverse AK plus 1 inverse, the result will be I want to multiply it on the left, so you can see. Well, it's actually not going to matter. I just wrote it down in the wrong order there. Then if I multiply this guy by this guy, we would get A1 through AK plus 1. These guys here will give me the identity. So I'll end up with AK times B inverse, but AK is B, and so I end up with the identity there. So it means that these guys up to AK plus 1 is invertible, and PK plus 1 holds. So any finite list of invertible matrices of the same size is also invertible if you take their product. The product is also invertible. Corollary. Like E1, E2, all the way down to En be elementary. Then their product is invertible. And we know what the inverse is. En inverse, En minus 1 inverse all the way down to E1 inverse. Yes.
Do we have to show the other side? Like multiplication on the other side? Or
Well, I said it's going to be similar.
Oh, okay.
So it's going to work out the other way.
Okay.
In fact, let me just state that. Because at some point it becomes annoying knowing that you have to prove both sides. Or you have to just mention that you're supposed to prove the other side. So it's actually, this is a theorem. Should be a theorem. Suppose A times B equals I, then turns out B times A will equal to I. So it turns out if you prove one direction, you can do this if and only. Let's just do it that way. This is true if and only if that is true. i.e., if we show something is invertible by left multiplication, it is automatically invertible by right multiplication. So technically, to prove that something is an inverse, you only need to verify one of the equations in the definition of the inverse. So when it comes to matrices, the left inverse is automatically the right inverse, it turns out. So you can be a little sloppy with the definition here because there's a theorem that says it will work in either order. Not going to prove that because we're going to get on to bigger things, but you can actually attempt to prove this. Probably good practice for the exam, to be honest. It shouldn't be too difficult once you sort of see the trick. And the proof should be very short. But I want to move on. To another theorem. Ultimately, we're going to build up to a part of the equivalence theorem. And we'll keep adding to it as the semester goes on. So we'll discover more things in linear algebra, and as we move on, we're like, oh, this we can add to the theorem. We're just going to keep stacking things on. By the end of the course, we have like 20 things in the theorem. But they're very useful things to know about, and they give us a lot of power. So the other thing I wanted to show is let A and let N be a matrix. Then the reduced row echelon form of A is either IN or has a row of zeros. This is true for any square matrix. There are only two possibilities for its reduced row echelon form in terms of.
Could it have more than one row?
Yeah, well, if it has two rows of zeros, then it also has a row of zeros, so yes.
Okay.
So you can interpret this has a row of zeros as at least one row of zero. proof here is also not too complicated. Find the RREF of A. Then, this is something I introduced before. Then the rank is either n or not. Right? It's either n or it's not, that's true. So if the rank is n, there are n pivots. And so one is in every column, and hence in every row. Right? It means that the reducer echelon form of that guy has to have a pivot in every single row and at the same time in every single column. Since it's in reduced row echelon form, it has zeros all below all the ones, but it also has zeros above all the ones by our definition. Right? So you've literally created the identity, and there's no other option at this point. Because we have to have zeros above and below all the ones. That gives you the identity matrix. And that's if the rank is n. If you have less pivots than there are rows, it means there's going to be some row that does not have a pivot. So you're going to end up with a row of all zeros. And that's basically it. Not terribly complicated, but it's a useful observation. Now know enough to prove the equivalence theorem.
I have a question.
Yeah.
Because I'm misunderstanding something. I thought for reduced row echelon form, for example, if you had a 5 and a row with all 0, like a 5 there instead of a 0. Yeah.
Okay.
So I'm a little unclear. That would still be in reduced row echelon form, or no?
Not according to our definition.
Okay.
Because that would be the first non-zero number in a row, and we require it to be a 1.
I see.
So if we ended up with a 5 here, we'll do an extra row operation to
reduce
divide
it.
that
Okay.
row by 5,
Okay.
and we'll get that.
Cool.
So based on our definition, it'll have to be a 1. That's the non-zero number in every row. Prove some other facts before we get to the theorem. And we'll throw this into the equivalence theorem at some point. Let A n by n be a matrix. Then A inverse exists. Do I need the equivalence theorem for this? I'm going to get away without proving that. I think we can get away with it. A inverse exists if and only if the determinant of A is not equal to 0. So this provides a useful check for knowing when something is invertible or not, if it's worth searching for the inverse. Turns out you can the only matrices that are invertible are the ones with non-zero determinants. So So in order to have an inverse, you have to be a square matrix with a non-zero determinant. No other matrix will have an inverse. Which way do I want to prove first? That is invertible. So I know it has an inverse. Then I say this without appealing to the equivalence theorem.
The multiplication gives you the identity.
The reducer or echelon form of A I do think I need it, because what I can say, it's not going to be completely clear here if I don't have the equivalence theorem.
Wait, can you say that you multiply it, right, and then you get back the identity?
I want to say if it's invertible, then its reducer echelon form must be the identity.
Yeah, and then after, can't you just do the cofactor expansion to find out the determinant?
No, but this statement has to be justified. To say it would be IN, how do we know it would have to be IN?
Definition of invertible.
You can't get that directly from the definition of the invertible. Yeah, I think I have to prove the equivalence theorem. Because then this sentence is not justified at this point. So scrap that, we'll come back to it. Let's actually prove a part of the equivalence theorem. Make our lives a little bit easier. What do I call it here? Theorem. The equivalence theorem. It's incomplete. Like I said, this list we're going to keep adding to it. But so far we can say some things. And it gets its name because it's an equivalence statement. It says the following are equivalent. So far we're going to have 4 things in this statement. We've had 4 so far. Which is going to allow me to prove this. So 1, A is invertible. 2, AX equals B has a unique solution. For every B. Column vector. Of the right size, of course. C. The reducer or echelon form of A is the identity, right? It's going to make me say that. And last one, A is a product of elementary matrices. Right. So when I prove this, I'll be able to state that sentence, and no one's going to be like, why is that? Okay, so do we remember what that statement means? The following are equivalent?
You get one, you get all the others?
You get one, you get all the others, and if you don't get one, you don't get all the others. They will all be true or all be false at the same time. So if you know one, you know all. And if you know that one is not true, you automatically know that all are not true. They will all be true or all be false at the same time. So if you have a matrix and you know it's invertible, you automatically know all these other things. And if you have a matrix and you know it's not invertible, you automatically know all these other things are false. Right? So if it's not invertible, your system will not have a unique solution. If it's not invertible, you will reduce to something that's not the identity. If it's not invertible, you cannot write it as a product of elementary matrices, etc.
Wait, Professor, I have a question about that thing, right? Could you say that because the inverse exists and that inverse can be represented as a strand of elementary matrices that are relate to corresponding?
Sure, but to be able to say that, you use statement 4.
Uh,
The fact that I can write this as a list of elementary matrices, and I know that the product of elementary matrices are invertible and I can just put them on the other side, is the statement that you just made. So let's actually show this. So do we remember how to prove an equivalence statement? What is the strategy here?
Do a chain of implications.
So to do the chain of implications. So I have to show that this implies that, this implies that, this implies that, and this implies all the way back to the front. So I have this chain of implication that has no break in it. It means that all will be true at the same time. So let's actually prove that. Let's show that 1 implies 2. Assume A is invertible. And we have the system AX equals B. Can you solve that system in a unique way? Turns out we can. Then we obtain since A inverse exists, right? Saying something is invertible, saying there exists an inverse matrix for that guy. So that's a matrix that's the same size as A, which means I can multiply it by A on any side. And so because A is on the left side, I'm going to multiply both sides on the left by A inverse. Multiplication of matrices is associative, so I can choose to multiply these two first, and that gives me the identity. Which means that my x value is this particular matrix times that particular matrix, right? There's only one solution. And in fact, it's guaranteed to be there because the inverse exists. I can do this manipulation. Multiply by both sides by the matrix multiplication will be defined because the dimensions will match up, and we're done. So if my A is invertible, this guy has a unique solution. In fact, I know exactly what the solution is. It's going to be the inverse matrix times the column, where the inverse matrix is on the left. Yeah?
how do we know that's unique? Do we have to show that?
No. Why would it not be unique?
Now, how do we know that there isn't another thing that's a solution to that?
Well, we know that inverses are unique. That's why. Did I say that, or did I prove that?
I think you stated it.
We stated it. Inverses are unique.
Okay.
So this is a constant matrix, right? It means it has numbers. It's not like things have variables here where we have to worry about, oh, what if the variable is this? These are all numbers. And if my matrix is a coefficient matrix, that has all numbers. Its inverse is going to have all numbers. They're going to be specific, real numbers. So if I multiply something with specific numbers times something with specific numbers, I get specific numbers. It's not going to be different.
So we can just take
But
that.
another way we can do it is that the inverse is unique. So the only way conceptually here you'll think of there potentially being more answers is if there's some other guy that I could have multiplied on the left by to solve for x. But it turns out there is no other guy. Inverses are unique. And I might have stated that the proof of that is not that difficult. Just assume that there are two. And then you can show that they're the same thing. Right? And if I want to make a detour. Let's say B is a inverse. Assume that C not equal to B is also a inverse. Right? Then what that would mean is that if I take A times B, I get the identity, and if I take A times C, I get the identity. Right? And A is invertible. So this means AB would equal AC, and since the inverse exists, I would get B equals C. So inverses are unique. And that's a common way to prove uniqueness, right? Pretend there are more than one of the thing and show that both the things satisfy the same property ultimately means that they have to be the same. So inverses are unique, and that would be a proof by contradiction, by the way. You'll say, oh, we assumed it was not the same, but it turns out it was the same contradiction. Okay. So this has a unique solution. Let's move on. 3. We now have to show that 2 implies 3. So the fact that this equation has a unique solution must imply that the reducer echelon form is IN. Why?
Because if you have a square matrix with less pivots than n, you will have to have.
You get parameters.
Yeah.
Right? So here, A must have n pivots. If I'm assuming it's n by n, since it must have a pivot in every row. So in other words, I'm saying that the matrix, if I have, I'm saying that if you augment these matrices A and B, and you reduce it, there should be a point where there's a 1 in every row that will match up to these guys here. Right? So because if there isn't a 1 in every row, it means that column gets to be a parameter, you end up with infinite solutions. As well as if you have a row of all zeros, then if that guy is non-zero, you'll end up with no solution, right? But we know the solution exists, so this case will never happen, and it's also not the case that you won't have a pivot somewhere else, because you'd have to be able to solve for everybody, right? So the rank is going to be n, which would allow us to it'll not be inconsistent because we know the solution exists, and the solution is given by that. But in order to not have infinite solutions, it must have a pivot in every row. But having a pivot in every row means you pretty much have the identity right here. And so the reduced row echelon form of A is equal to the identity of size n. How about 3 implies 4?
You could
Right? Yeah, what would you say?
let E1 be an elementary matrix. Well, no, never mind.
Well, you're on the right track, but you'll potentially need more than one. Like E1 through EM represent the row operations needed to reduce A to IN, right? We did a bunch of row operations to get here. Now we know that each row operation is just multiplication by an elementary matrix. This means that if I take A and I apply E1 to it, that's me doing a row operation. Then I do another row operation. Then I do another row operation. And I do a bunch of row operations. If I do m of them, ultimately that results in the identity. Now how can I say that A is a product of elementary matrices? I want to be able to say A equals a multiplication of elementary matrices.
Well, since we defined that the reduced row echelon form is an identity matrix, then those are equivalent. I mean, IN, the reduced row echelon form is of A is IN, which means
Right, that's what this is saying.
right.
What you could do is write.
Ultimately, I want to be able to say A is equal to, and I want to multiply it by a bunch of things here, C1, C2, Cn, where each of these are elementary matrices. How can I get to that statement?
You write IN equal to the product of the elementary matrices needed to get to reduce row echelon form and their inverse.
The inverse is going to be.
Because
How do you know the inverse is going to be used?
the inverses are
You proved it.
elementary.
Yeah, we showed that the inverse of this exists and is, what is it? The product of the inverse is in the opposite order. So, what we can do then is if EM all the way down to E1 times A equals the identity, I can multiply both sides on the left by the inverse of this guy. Right? So if this equation holds, multiply both sides on the left by that guy. This guy is going to cancel and give me the identity, so I'm going to end up with A equals. This guy, I know, is a product of these guys. So it's E1 inverse multiplied by EM inverse times I. But saying a bunch of the things times I is just saying those things. Right? It's just E1 inverse times EM inverse. And we know that the inverse of an elementary matrix is also an elementary matrix, and so A is a product of elementary matrices, because it's the product of inverses of elementary matrices. And each EI inverse is elementary. Now, finally, let's go from 4 back to 1. How are we going to do that? So assume I can write A as a product of elementary matrices. How can I know that A is invertible?
Did we show that elementary matrices are always invertible?
Isn't that like the backward version of that?
It's kind of the backwards version of this, right? So, but we have to start from the other side. So assume A is, and these are different E's potentially, right? So E1 through EM multiplied, right? Because that's our assumption. Then I can multiply it. I know the inverse here exists. And so I can multiply both sides on the left by this inverse. 1 through En. Right? Now multiplying this by its inverse gives me the identity by definition of what the inverse is. And so what that means is that here's a matrix A, and I multiply by something, let's call it B, and I obtain the identity. This means B equals E1 through En. Inverse is the inverse of A. That completes the proof. So a lot of ideas came together to make this proof, and the proof itself is going to be important to bring a lot of other ideas together. Very incomplete, but as for now we have these 4 steps, and so now that thing I mentioned earlier is just a corollary. A is invertible if and only if the determinant of A is not 0. Proof. Assume A is invertible, then by the equivalence theorem, its reduced row echelon form is the identity. But then, throwing back to the concept that we had at the beginning, row operations can only scale a determinant. And so the determinant of A must be not 0 since the determinant of I is not 0. Right? If I started off with something whose the determinant was 0, the determinant of the whatever guy I did operations on to get the new guy, his determinant would have to not be 0, because row operations is only going to be multiplying the determinant by some non-zero constant factor the whole time. Converse is similar. If you assume the determinant of the original was 0, then you would it cannot be reduced to the identity because the reduction of the identity is not 0. It would reduce to a matrix in the other way according to our theorem, right? Do I want to write it for the converse? Assume A is not invertible. Right? So if I assume it was invertible, the determinant was non-zero. Now let's assume it's not invertible. Then the reduced row echelon form of A is not the identity, right? By the equivalence theorem. Which means, by a previous theorem, we proved a theorem earlier today, that the reduced row echelon form of a square matrix is either identity or it has a row of zeros. And that means which means if I take the determinant of this reduced form I would get 0 because it has a row of zeros, just expand along that row. I would multiply all cofactors by 0, which means the determinant of A is 0 itself, since row operations scale the determinant. This means we can add more to the equivalence. The following are equivalent. We can say 1, A inverse exists. 2, AX equals B has a unique solution. 3, the reduced row echelon form of A is the identity. 4, A is the product of elementary matrices. And 5, the determinant of A is not going to be 0. All these things will connect. If you know one, you know all. So in other words, I can have some really complicated multi-dimensional linear transformation, and I want to know, is it 1-to-1, or is it invertible, which would also mean it's 1-to-1 and onto. And all I have to do is represent that guy as a matrix and find the determinant. And I'll automatically know about the properties of that function. And knowing about the properties of the function tells me about the properties of the sets and blah, blah, blah. So the equivalence theorem is pretty important, and that's one thing. And we'll add to that as time goes on. We're actually behind time, so let's see if I can show you at least one method for finding the inverse, and we'll do the other one the next time. And we're going to use this as the idea. This is going to be the inspiration for this method. So now we're going to look at finding the inverse. It's one thing to know it exists, but what is it? We'll cover two methods.
Professor,
Yeah.
is this still 2.2?
Yeah. Yes, I think so. Yeah. When I start talking about symmetric matrices, I'm no longer in 2.3. That's back in 1.4 or 5. Okay. We'll cover two methods. One is the row reduction method. It's the one that falls into our lap by the equivalence theorem. So I'm going to show you that one first because it's immediately, I don't have to justify it too much. 2, using something called the adjoint method. So we're going to create a matrix that we call the adjoint matrix for the matrix A, and I'm going to use that to find the inverse. But it has a weird definition. It's the transpose of the matrix of cofactors, and we'll talk about that. This one, though, falls right into our lap by the equivalence theorem. 1, row reduction. Since we know if A is invertible, then if I take E1, E2, multiply by En times A, I will ultimately get the identity matrix. Right? This means that E1 up to En is the inverse of A. Right? I'm going to throw something in here, but it's not wrong to say it. It's going to be the basis of our method. I can just say this is multiplied by I. Right? Which doesn't change the answer. Right? So it turns out the inverse is going to be the identity times these guys. So in other words, what am I saying? These guys are the operations used to find the RREF of A. Notice that if I do exactly the same operations on the identity, I get the inverse. i.e., the same operations on A to obtain IN or will be the same operations on IN to obtain the inverse. So figure out what I did with A to find this reducer echelon form, do exactly the same thing to the inverse, and that will give me the, do the exact same thing to the identity matrix, and that will give me the inverse. That leads us to the method, which I'm going to describe in a nutshell. Here's a matrix that I want to be able to find its inverse, augmented with the identity. What do I do now? Do a bunch of row operations. The goal would be to find the reducer or echelon form of A, which because it's invertible by assumption, what should that be? It's going to be the identity, right? So I'm going to do a bunch of operations. So here, find the reducer or echelon form. I know it's going to end up being the identity. So it's going to involve a bunch of row operations, E1 through En. But if I start out with the identity, do exactly the same operations, what does that end up being?
A inverse.
A inverse by this. Which means to find an identity, I can set up this augmented matrix and just reduce it. At the point where the identity appears on the left, the guy that appears on the right is going to be the inverse of the original guy. So it just comes down to doing a row reduction. Create this giant matrix, find the reducer echelon form. Your identity appears on the right side. Your inverse appears on the right side. So once the identity shows up here, boom, the guy that's there is your inverse. Let's actually do some examples. Start out with a simple one, 2 by 2. Or reuse example 1, 2, 3, 4. Let's find the inverse of the matrix 1, 2, 3, 4 using this method. There's a formula to find the inverse of a 2 by 2. Does anyone know that?
You have to use the determinant.
It's 1 over the determinant times this thing where you swap these two and you change the sign of those two. That formula comes from the second method that I'm going to tell you. The adjoint method is how we know how to do that. But you won't really see that here. But let's actually do this using row reduction. Let's check your answer. So, how do we do it? Well, set up the augmented matrix. 1, 2, 3, 4, augmented with 1, 0, 0, 1. And we're going to find the reducer echelon form. So, remember the goal, establish the first pivot. It's going to be this guy. It's already a 1. Let's leave him alone for now. We'll kill the 2 later. I want to immediately make this a 0. So what can I do to create a 0 there?
Multiply row 1 by -3, add it to row 2.
Yeah, so I'm going to take row 2 minus 3 times row 1. So this minus 3 times that is 0. This minus 3 times that. Minus 2. This minus 3 times that. This minus 3 times that is that. Now, I'm going to want to make a pivot here. Dividing by -2 at this point gives me a fraction, so I'm going to avoid that for a bit. So I turn my attention to killing the 0 above that, which I can do by just adding the rows. Take row 1 plus row 2. This plus this, 1. This plus this, 0. This plus this, -2. This plus this, 1. Now I have 0, -2, -3, 1. Now there's nothing else to do but to make this into a bona fide pivot, so I'm going to divide the second row by 2, -2. So this gives 1, 0, -2, 1. Then I'm going to just divide this guy by -2. See this guy right here? That's your A inverse, because the identity is now on the left side. So I claim that that's the inverse matrix. Let's actually check that. So I set up the augmented matrix, put the identity on the left, find the reduced echelon form. If this guy's invertible, which I know it's invertible because the determinant is not 0, so I wouldn't even try to do this if the determinant was 0. But knowing that the determinant here is not 0, in fact the determinant is 4 minus 6, so I know the determinant is -2. I can do this, find the reduced echelon form. It will give me the identity on the left by the equivalence theorem. The guy on the right will be the inverse by the corollary of the equivalence theorem. And so now let's check. Multiply this guy. It doesn't matter what side I multiply on because we have that theorem that says if you multiply in any order, it should work. So I'm going to multiply this by 1, 2, 3, 4. The result should be the identity. Let's do the matrix multiplication. This is -2 times 1 plus 1 times 3. -2 times 2 plus 1 times 4. Here I would have 3 over 2 times 1 plus -1/2 times 3. Here I would have 3 over 2 times 2 plus -1/2 times 4. And so what do I have here? 3 minus 2 is 1. This is -4 plus 4, that's 0. This is positive 3 over 2 minus 3 over 2, that's 0. And this is 3 minus 2, 1. So that's our guy. Right? So that's the inverse. Give it a slightly bigger matrix now, and we'll end with this example. One minus 2, 3, 2 minus 1 minus 1, minus 3, 1, 4. So this is now 3 by 3. Which you don't have a nice little neat formula for, so let's actually just do it by row reduction. We'll learn another method next time. And in general, I don't care which method you use, so if you want to use, if you like the row reduction method, do the row reduction method. If you don't, you can do the other one.
Will you tell us beforehand, like if it is possible, like if it's invertible, or do you?
It depends on the problem.
Okay.
But you should know, based on the equivalence theorem, whether it's possible or not. And usually if I ask you to find it, it exists, right? So if I say, here's a matrix, find the inverse, I can say that, you know it exists, so you just jump into a method to search for it.
I don't know if they're like trick questions or something.
I think you'll kind of, you should know. If you know the equivalence theorem, then you'll know. So here's a method. We're going to do this guy. Just practice our reduction skills because that's definitely coming up. And of course, you augment it with the identity matrix of the right size. So it's a 3 by 3 matrix. So I'm going to augment it with the 3 by 3 identity. Now we're going to do row reduction. This guy has a 1 already, so I'll leave that for now. I'm immediately going to want to get zeros below it. So how can we get that? I can do row 2 minus 2 row 1 to get a 0 here. And I can do row 3 plus 3 row 1 to get a 0 there. So let's do that. Row 2 minus 2 times that, 0. This minus 2 times that is what, minus 3?
It would be
Or plus
positive.
This minus 2 times that is a minus 7. This minus 2 times that, minus 2. This minus 2 times that is 1. This minus 2 times that is 0. Now this plus 3 times that is 0. This plus 3 times that is minus 5. This plus 3 times that is 13. This plus 3 times that is 3. This plus 3 times that is 0. This plus 3 times that is 1. Now I'm going to want to make this guy the next pivot. Divided by 3 at this point, though, is going to get me fractions because the 7 and the 2 and the 1, because of everyone else. So at the moment, while I know I'm going to eventually divide by 3 to make that a pivot, I'm not going to do it just yet because I don't want fractions. But I know I'm going to want to get a 0 here. So right now, my goal is to just figure out how to get a 0 there. And how would I get a 0 there? So I'm going to leave the first row for a second. What I can do, I'm going to make these the same magnitude, right? So I can multiply the second row by 5, multiply this row by 3. They'll both be 15 with an opposite sign. Then I'll add them and kill this guy. So let's do that. Let's do row 2 times 5. I'm going to do row 3 times 3. That's 0. 5 times this is 15. 5 times that is minus 35. 5 times that is minus 10. 5, 0. Multiply this by 3. 0. 5 times that is 3 times that. 3 times this. 3 times this. 3 times this. 3 times this. These guys are the same. Let's kill that guy by just adding them. Let's put the smaller version of row 2 here. At this point, I'm going to take row 2 and add it to row 3. That'll give me 0, 0. That'll give me a 4. That'll give me a minus 1. That'll give me a 5. That'll give me 3. Now I know I'm going to want to make this guy a pivot as well, but I don't want to get fractions yet, so let's leave it for now. Eventually what I'm going to want to do is all these guys here, I'm going to want to make zeros. So I'll start working on them one by one. Let's work on this guy. How do I make that 0? Multiply this by 3. And I multiply this by 2. Add these guys. this guy is fine. These two are fine, I'm just waiting to divide them because I don't want to get fractions yet. So now let's kill these two. So this one's going to take a while. I'm going to create the same things here. So what can I do here? Let's leave this as 0 minus 5 for the moment. How about multiply this by 4, multiply that by 7. 4 7 is 28. This by 7. And now let's add those guys. So this is 3, 0, minus 5, minus 1, 2, 0. Gonna add these two, so that's 0, 12, 0. Add these two, I get what? Minus 15. Add these two, I get 39. Add these two, I get 21. What else do I need to do here? I need to kill that guy. So let's multiply this guy by 4. And multiply this one by 5. We're almost there now. So, and now I'm going to add these two, so that's 12, 0, 0. This will be minus 9. 25 plus 8 is what, 33? This plus that is 15. 0, 12, 0. 15, 39, 21. 0, 0, 4, minus 1, 5, 3. One last step, let's make all these guys pivots, turn them into the identity. So I'm going to divide this by 12. This is row 1 divided by 12. I'm going to divide row 2 by 12 as well. And row 3 I'm going to divide by 4. So 9 over 12 is minus 3 over 4. 33 over 12. Is that 11 over 4, 15 over 12 is 5 over 4. Then divide this guy by 12. So that's going to give me minus 5 over 4. Divide this by 12. It's going to give me 13 over 4. Divide this by 12. It's going to give me 7 over 4. Divide this by 4, minus 1 over 4, 5 over 4, 3 over 4. And that is why I allow scientific calculators. And that is also the inverse of the matrix A, provided we did not make any mistakes, but we're not going to check it. That's left to you. I'll see you guys tomorrow. Remember, our test is on Thursday. I'll also post some stuff too. After tomorrow, it'll cover everything we cover up to tomorrow. And so after tomorrow, I'll post like a review of things that you should look for. So let me stop the camera. Sure.